Welcome to this project presentation on iris species classification. In this project, we will walk through an end-to-end supervised machine learning workflow using the iris dataset. The objective is to predict the species of an iris flower using its feature measurements. By the end of this walkthrough, you should understand not only how the model is built, but also why each step matters in a machine learning project. The main objective of this project is to classify an iris flower into one of its three species: Setosa, versicolor, or virginica. The model uses four numerical input features, which are the flower sepal and petal measurements. Since the target has three possible classes, this is a multiclass classification problem. The learning goal is to understand how a supervised classification flows from raw data to a final prediction pipeline. Here we see the full project flow. We begin with the machine learning setup, where we import libraries and define reproducibility settings. Then we load the iris dataset and perform basic data quality checks. After that, we move into exploratory data analysis. This helps us understand feature distributions, class separation, correlations, and possible modeling signals. Once the data is understood, we define a modeling strategy. We split the data into training and test sets, compare models using cross-validation, and select the best final model. After model selection, we evaluate the final model on the untouched test set. Finally, we explain model errors, inspect feature importance, and use the model to predict new flower examples. The iris dataset contains 150 observations. Each observation represents one iris flower. There are four numeric predictors: sepal length, sepal width, petal length, and petal width. The target variable represents the species of the flower. There are three species: Setosa, versicolor, and virginica. Each class has exactly 50 observations, so the dataset is perfectly balanced. This balance is useful because accuracy becomes a reasonable headline metric. This dataset is small and clean, which makes it a good benchmark for learning the complete supervised classification workflow. Before building any model, we set up the notebook for reproducibility. The project uses standard Python machine learning libraries such as NumPy, Pandas, scikit-learn, and visualization libraries. A fixed random state is used so that train test splits, cross-validation shuffling, and stochastic model behavior can be repeated. A very important design decision is the use of scikit-learn pipelines. For example, when we apply standard scaling before logistic regression, the scaler is placed inside the pipeline. This prevents data leakage. During cross-validation, the scaler is fitted only on the training fold and then applied to the validation fold. The main idea is that good machine learning notebooks should be repeatable, auditable, and safe from accidental leakage. Before modeling, need to check whether the data is suitable for analysis. The Jupyter Notebook checks data types, missing values, unique values, duplicate rows, and class balance. All four predictor columns are numeric, and there are no missing values. The target is also clean and balanced, with 50 observations for each species. There is one exact duplicate measurement and label combination. In this project, it is retained because the iris dataset is a benchmark dataset and does not contain a unique row identifier. Without an identifier, we cannot confidently say whether it is a duplicate record or simply two flowers with the same measurements. The main takeaway is that data quality checks should always be explicit, even when using a clean benchmark dataset. Descriptive statistics help us understand feature ranges, scale, and possible discriminating power. The sepal measurements have smaller variation, while petal length and petal width show much larger spread across the dataset. This is an early signal that petal measurements may be more useful for separating species. The box plots confirm this visually. Setosa is clearly separated by petal dimensions, while versicolor and virginica show more overlap. Sepal width appears to overlap heavily across classes, which suggests that it may be the weakest standalone feature. This step is important because it allows us to build modeling expectations before training any model. The pair plot shows how features interact with each other. Looking at individual features is helpful, but combinations of features often reveal stronger class separation. In this project, Setosa forms a very distinct cluster, especially when petal length and petal width are plotted together. Versicolor and Virginica are more difficult to separate because they share a boundary region in the petal feature space. This visual insight is important because it predicts what we should expect later in the confusion matrix. We should expect setosa to be classified easily, and most errors, if any, should happen between versicolor and Virginica. Now we combine two useful ideas: feature correlation and feature relevance. The correlation heat map shows that petal length and petal width are highly correlated. This means they carry related information. The ANOVA F-score analysis shows that petal length and petal width also have the strongest relationship with the target classes. So the petal features are both powerful and somewhat redundant. In a larger project, we might consider feature selection or dimensionality reduction. But here, the dataset has only 4 predictors, and regularized logistic regression can handle this level of redundancy. Therefore, all 4 features are retained in the modeling pipeline. Here we discuss on the modeling backbone of the project. The full dataset has 150 rows. We use a stratified 80-20 train test split. This gives 120 training rows and 30 holdout test rows. Stratification ensures that each species remains equally represented in both training and test sets. Model comparison is performed using 5-fold stratified cross-validation on the training set only. This is important because the test set must stay untouched until the final evaluation. The models compared include logistic regression, k-nearest neighbors, random forest, and a dummy baseline. For models that require scaling, such as logistic regression and k-nearest neighbors, scaling is kept inside the pipeline. This keeps the process leakage safe and repeatable. Now we have the cross-validation results. Logistic regression and k-nearest neighbors both achieve a mean cross-validated accuracy of 0.958, with a macro F1 score of 0.958. Random forest is very close, with a mean accuracy of 0.950. The dummy baseline performs much worse, with an accuracy of 0.333. This confirms that the trained models are learning real patterns from the features. Logistic regression is selected as the final model. It is not selected because logistic regression is always the best model. It is selected because, in this project, it matches the strongest validation performance while also being simple, probabilistic, and easier to interpret. After selecting logistic regression, the final pipeline is fitted on the full training set and evaluated once on the untouched holdout test set. The model achieves a test accuracy of 0.933, meaning it correctly predicts 28 out of 30 test examples. Setosa is classified perfectly. This matches what we observed earlier in the exploratory analysis, where setosa formed a clearly separated cluster. The 2 errors are symmetric. One versicolor flower is predicted as Virginica, and one Virginica flower is predicted as versicolor. This also matches the visual analysis, where versicolor and Virginica overlap near their decision boundary. Because the test set has only 30 examples, the confidence interval is wide, so we should avoid overclaiming the precision of the final accuracy. Accuracy tells us how often the model is correct, but error analysis tells us how the model fails. In this project, both incorrect predictions are low-confidence errors. One Virginica sample is predicted as versicolor with a confidence of around 0.515. Another versicolor sample is predicted as Virginica with a confidence of around 0.557. These are borderline predictions, not confidently wrong predictions. This is an important interpretation. It means the model is uncertain because the samples are close to the class boundary. In a real operational system, we could use this kind of confidence information to route uncertain cases for manual review. However, any threshold would need to be validated on more data. Here we have the feature importance using permutation importance. Permutation importance is a model-agnostic technique. It works by randomly shuffling one feature at a time and measuring how much model accuracy drops. If shuffling a feature causes a large drop in accuracy, that feature is important for the model. In this project, petal width has the highest importance, followed by petal length. Sepal width and sepal length contribute less independent information. This result reinforces what we already saw in the exploratory analysis. Petal measurements are the strongest predictors of iris species. However, feature importance should not be interpreted as causation. Also, Because petal length and petal width are highly correlated, they can partially substitute for each other. After evaluation, we use the fitted model to predict new flower examples. The examples include 3 class-typical flowers and 1 deliberately ambiguous boundary case. For class-typical examples, the model gives high-confidence predictions. The setosa-like example is predicted as setosa with high probability. The versicolor-like and virginica-like examples also receive strong support for their predicted classes. The boundary case is more interesting. It is predicted as virginica, but with only 0.571 confidence. The probability for versicolor is also relatively high. This shows why probabilities are more informative than labels alone. A predicted label gives the final class, but the probability distribution tells us how confident the model is. In practical applications, low-confidence predictions should be treated carefully. Now we summarize the reusable machine learning code pattern from the project. First, load the data and separate predictors from the target. Second, protect a final test set using a stratified train test split. Third, build a leakage-safe pipeline. In this project, the pipeline includes standard scaling followed by logistic regression. Fourth, use cross-validation on the training set to compare models or tune hyperparameters. Fifth, fit the selected model on all training data, evaluate it once on the test set, and then interpret the results. This pattern is not limited to the IRIS dataset. The same structure can be reused in many tabular classification projects. For real-world use, we would also add stronger validation, monitoring, drift checks, and model versioning. This project successfully demonstrates a complete supervised classification workflow. The main conclusion is that petal length and petal width provide the clearest separation between IRIS species. Scaled logistic regression matches the best cross-validation score, with a mean accuracy of 0.958. On the holdout test set, it achieves 0.933 accuracy, correctly predicting 28 out of 30 examples. The errors are low-confidence confusions between versicolor and virginica, which is consistent with the overlap observed during exploratory analysis. However, there are limitations. The dataset is small, curated, and balanced. The test set has only 30 observations, so the accuracy estimate has uncertainty. As next steps, we could validate the model on a larger external dataset. Thank you for following this IRIS species classification project walkthrough. In this project, we covered the complete machine learning flow. The Jupyter Notebook with the full code, visuals, and step-by-step explanation is available on Kaggle and GitHub. I will share both links in the video description. Thanks.